Here's the next question, number 36. In the balanced three-phase 50 Hz circuit shown below, the value of inductance L is 10 millihenry. The value of capacitance C, for which all the line currents are 0, in millifarad is dash. Okay, so please forgive my very rough diagram. It is supposed to be a delta connected connection of inductances and a star connection of capacitors in the center. Okay, so this is what we are supposed to do. Now we have been given the inductance value and we have to find the capacitance value. So since the capacitors are connected in star, it is important for us to convert it into delta form so that for each branch we have a parallel of inductance and capacitors. So what happens here is, I'm going to do my best and try and draw this as clearly as possible. We have an inductor, we have a capacitor in parallel. So this is how we are supposed to convert it. We have our capacitor here and inductor here. Okay. So this is what we have to convert the figure into. In order to do this, all we have to do is convert the star connection of the capacitors into delta form. When we do that, the value of C becomes C by 3 in each of these cases here. We have so C by 3, C by 3, C by 3. L remains the same as it is. Okay, so this is our circuit. Now we have that the frequency is 50 Hz and the question also tells us that all the line currents are supposed to be 0. So that's our clue. Now for the line currents to be 0, that is only possible when the inductor and capacitor pair is resonant at this frequency given 50 Hz. So that means that we can use the relation of 2 pi f is equal to root 1 by LC or 1 by root LC. So 2 pi f is equal to root of 1 by LC. This is going to be our relation when the circuit resonates at f is equal to 50 Hz. So it is resonant at 50 Hz. We have our value of f, we have a value of L, we substitute the values and we solve for C. At times you will have to just remember certain formulas. So we have omega is equal to 1 by root LC. This is at resonating at f is equal to 50 Hz. So omega is 2 pi f. So 2 pi f is equal to 1 by LC. So let's rearrange the formula to find out what the value of C is. Oh, but there's another thing. You will have to remember that C is not just C anymore. Now because we have converted the star into delta, C has become C by 3. So this is really C by 3. So now if we rearrange and equate it in a way to find out what C is, we get the formula as C is equal to 3 by L, just cross multiplying and then squaring on both sides, and this is what we get. Okay, C is equal to 3 by L into 1 divided by 2 pi f whole square. Let's just check. If we cross multiply, you will get the root LC by 3 here and 1 by 2 pi f and then squaring on both sides. Yes, this is it. So C is equal to 3 by L into 1 by 2 pi f whole square. So we have the value of L given to us. L is 10 millihenry. So that's 10 into 10 power minus 3. F is 50. So that becomes 100 pi whole square. So C is equal to 3 divided by 10 into 10 power minus 3, 1 by 100 pi square. Now I will leave the simplification to you. The final answer though is 3.03 millifarad. So here's our final answer, 3.03. I hope this has helped. Here's the next question, number 37. In the circuit shown below, the initial capacitor voltage is 4 volts. Switch S1 is closed at t is equal to 0. The charge in microcoulombs lost by the capacitor from t is equal to 25 microsecond to t is equal to 100 microsecond is dash. Okay, so we don't have options here. We will have to try and work it out. Okay, in the circuit given, we see a switch which is open, S1, and it's being closed at t is equal to 0. And we also have the capacitor at a voltage of 4 volts. The capacitor voltage is 4 volts. And the value for the capacitance is 5 microfarad. So that's what's given to us, and we have to find out the charge. So to begin with, let's write down what's given, just to have it all clear. VCI is equal to 4 volts. And then we have time from t is equal to 25 microsecond to t1 and t2 is equal to 100 microsecond. Now for this equation, let's write down what is the current equation when the switch is closed. Now this is important because this is a standard formula. I of t, this is when the switch is closed, is equal to V by R e power minus t by tau. This is important. Now here tau is RC. Okay, so let's substitute that over here. We have I of t is equal to V by R into e power minus t by RC. So we have the value of R, we have the value of C, and we also have the value of V. Let's substitute all of that in and see what we get for now. So we have I of t is equal to V is 4 divided by R is 5, e to the power of minus t divided by RC. So that's 5 into 10 power minus 6, because this is 5 micro. Okay, so 5 into 5 into 10 power minus 6 is 25 into 10 power minus 6 seconds. So that's in terms of time, tau. So we have t divided by 25 into 10 power minus 6. Let me just write this down here now. Okay, so the equation we have is I of t is equal to 4 by 5 e power minus t by tau is 25 into 10 power minus 6. Alright, now the question tells us that we have to find out the charge. Charge is the integral of current. If we integrate current, that is what we get. So to find out the charge lost, Q is equal to T1 to T2 I of t dt. Okay, so we have what T1 is, we have what T2 is. Let's substitute it all. We will get integral of 25 microseconds 10 power minus 6 200 into 10 power minus 6 of I, which is 4 by 5 into e power minus t by 25 into 10 power minus 6 dt. Okay, let's take the constant out and integrating, let's see what we get here. We'll get 4 by 5 into e to the power of minus t into, now since this is 1 divided by 25 into 10 power minus 6, I'm just going to write it as 0.04 into 10 power 6. What I've done is just divided 1 by 25 into 10 power minus 6 is 0.04 into 10 power 6. divided by 0.04 into 10 power 6. This is at 25 10 power minus 6 to 100 into 10 power minus 6. We have to be careful with these powers here. Alright, so now we have this expression after we have integrated. Okay? So once we have done this, let's substitute the upper limit and the lower limit. Now when we substitute this in terms of t, you will have 4 by 5 into e to the power of minus 100 into 10 power minus 6 times 0.04 into 10 power 6 divided by 0.04 into 10 power 6. I hope you're able to follow what I'm writing here. They might seem a teeny bit small, that's why I'm reading it out so that you can follow. Minus e to the power of minus, now we have the lower limit, 25 into 10 power minus 6 into 0.04 into 10 power 6 divided by 0.04 into 10 power 6. Okay. So this is the expansion. Substituting the upper limit first and then the lower limit. So I hope you can see that. It might seem a little close, but this is the power of e. E to the power of minus lower limit times 0.04 into 10 power 6. Now I will leave the simplification to you because it's just it's basic algebra. You can use your calculators to enter the values and find out. We'll get the final answer as 6.99 into 10 power minus 6 coulomb. 6.99 into 10 power minus 6. Now that is our final answer. Let me just, yeah, okay. Now it's been asked for microcoulomb, so we don't have to put in into 10 power minus 6, we just put in 6.99. 6.99 into 10 power minus 6 is microcoulomb, so it's just 6.99. I hope this solution has helped. Here's the next question, number 38. The single line diagram of a balanced power system is shown in the figure. The voltage magnitude at the generator internal bus is constant and 1 pu. The pu reactances of different components in the system are also shown in the figure. The infinite bus voltage magnitude is 1 pu. A three-phase fault occurs at the middle of line 2. The ratio of the maximum real power that can be transferred during the pre-fault condition to the maximum real power that can be transferred under fault condition is dash. So here we don't have, it's not a multiple choice question, we have no options, so we will have to try our best and work it out as much as possible. So the question asks us to find out the ratio of the maximum real power that can be transferred during pre-fault condition. So that's power at pre-fault to the maximum real power that can be transferred under faulted condition. Power at faulted condition. This is the ratio that we are asked to find. Alright, so there are a couple of steps, quite a number of steps that go into solving this problem. Let's work it out. First, we need to calculate the maximum power at the pre-fault condition, that is before the fault has taken place. So before the fault has taken place, let's try and resolve this into an equivalent circuit. So when we do that, we see that we can add up these two impedances given, J.1 and 0.5, since they are in series. So that's J.6 for this line, and here it's J.6 as well. Note that the question says that the fault occurs somewhere in the middle of the second line. Okay, so we'll come to that in the second step. So the first step, let's write down, okay, this is without fault, without the fault occurring, or pre-fault. Okay, and this is the equivalent circuit. Let me just draw that. So we have, this is for the first line, this is for the second line. Here we have our infinite bus, grounded. Okay, so we have been given that it's 1 pu here, 0.2 here. We calculated this as 0.6 for the first line, 0.6 as the second line, and the infinite bus is at 1 pu. Okay, so this is our equivalent circuit. If you notice, it has all the components written here. Okay, so let's find out what is the power at pre-fault. At pre-fault condition, now our general power formula in terms of voltage and impedance is V square by Z. So let's use the same thing. We have 1 pu square divided by the resultant of all these three impedances that we have here. Now 0.6 and 0.6 are in parallel, 0.2 is in series to this part. So here Z would be 0.2 plus parallel of these two, which would be 0.6 into 0.6 divided by 0.6 plus 0.6. Now if we are to solve this, 0.6 into 0.6 divided by 0.6 plus 0.6 gives us 0.3. So here Z would be 0.2 plus 0.3, which is 0.5. Substitute that over here, 0.5. 1 by 0.5 gives us a power of pre-fault as 2. So we'll keep this aside. So this is the numerator part of the ratio that we are supposed to find out. Now the next part is to find out, to evaluate the circuit when the fault occurs. Okay, so this is with fault or during fault. Second step, during fault. Now during fault, we'll draw the equivalent circuit. Okay, let's see now what we have. Okay, so the question says that the fault occurs somewhere in the middle of the second line. So when it occurs in the middle of the second line, the impedance is split into two. Now you can take any two values, but make sure that the values correspond to the fault occurring somewhere in the middle. So because the word middle is used, I'm going to split this 0.6 into 0.3, 0.3. Please observe. Here's our infinite bus, 1 pu, and this is 0.2, this is 1 pu, and here we have J0.6. Okay, so the fault has occurred somewhere in between, in the middle of the second line. So I have split this impedance into two parts. So here we have 0.3 and here we have 0.3. You can consider it as 0.2 and 0.4 if you like, or 0.25 and 0.35, any way that actually adds up to 0.6. But make sure that it is not too much of a difference, because the question says that it happens somewhere in the middle. Okay, so now we have a few things to do. This is in the form of delta. You will see that it is in delta form. So first we have to convert it into star form, a star connection, and then convert it back into delta in order to form a pi connection. We'll do it step by step. Okay, so the first thing is to evaluate this portion here and convert it to star connection. So we are trying to resolve this entire thing as much as possible. So the first step is to convert this into star connection. So in order to do that, you will have to recall the basic formulas of conversion of delta to star and then star to delta. I'll put it down here. Okay. So I'm going to note this down in the general delta shape. Okay. So we have 0.6, we have 0.3, we have 0.3. So this is the general delta shape. I've just converted that part, taken only the part that we need to convert. Okay. And we need to convert this into star form. Okay, let's call this R1, R2 and R3, and correspondingly here we would have, this is RA, this would be RB and this would be RC. So we know the conversion formulas. The formula is R1 is equal to RB RC divided by RA plus RB plus RC. Similarly, R2 would be RB RA divided by RA plus RB plus RC, and R3 would be RA RC divided by RA plus RB plus RC. Okay, so we have our values here and we can calculate what R1, R2, R3 is. Plug in the values. You will find that R1 is 0.15, R2 is also 0.15 and R3 is 0.075. Okay, so if we were to write this in the equivalent form in the circuit, please observe. Okay, so we are converting this delta connection to star. So this is what we get here. That's 1, 2 and 3. That's our infinite bus 1 pu, and that's 0.2, J.2, that's 1 pu. Okay, so this is our star of what we have converted. So here we have R1 at J.15, and then we have R2 which is also J.15, and here we have R3 at J.075. Alright, so now these two impedances are in series, so we can just add them to give us one value. So this is what we get now. This is 1 pu, this is J.075, this is 0.15, and here this is 0.2 plus 0.15, that's J.35, and here we have 1 pu. Okay, so from here this is what we have. Now you will notice that we have a star connected form here with 3 impedances. Now we cannot solve this because we have one impedance here which is connected to the infinite bus, and we have one which is grounded and one here which is connected to the source. So the next step is to convert this into pi form, or back to back to delta. So this entire thing, converting it back to delta form. So basically we need the form in like so. We have one here and then one here, one here. So this is 1 pu, this is 1 pu. We need it this way. This is because when a fault occurs, the second line would be grounded immediately. So the remaining impedance is what we have to calculate the maximum power that passes through that particular point. So since we don't have that in the first equivalent circuit, we have to try and resolve it as much as possible in order to get it into pi form. That's the ultimate aim here. Alright, so we need the values of these three impedances. Let's call this as RA, this as RB, and this as RC, and the values of the above circuit as R1, R2, and R3. So we are converting that into this using this formula right here. So you know how to do it when it is from delta to star transformation, but now we'll have to do it from star to delta transformation. So star to delta, I'll write down one formula, you can do the rest. RA would be R1 R2 plus R2 R3 plus R3 R1 divided by R1. So RB would be R1 R2 plus R2 R3 plus R3 R1 divided by R2, and RC would be, the numerator would be same, divided by R3. Okay, so that's basically the formula. Once we have this formula, we can substitute the values from the previous equivalent circuit here. R1 is 0.35, R2 is 0.15, and R3 is 0.075. So we'll have the values of RA, RB, and RC. So let me just flip this over and work it out here. Okay, so now the values of RA, RB, and RC according to the formula and the previous equivalent circuit that I've noted down. RA is 0.257. I will leave the substitution and the working out to you. I'm giving you the values so that you can work it out and check. So RA is 0.257, RB is 0.6, and RC is 1.2. So our circuit now becomes as such. Let me just show you. We have so here this is 1 pu. This is 1 pu, this is J1.2, this is J.6, and this is J.257. Alright, so now we concentrate on the impedance here of the line. So the power at faulted condition, okay, at faulted condition would be equal to V square, that's 1 square, divided by 1.2, and that results in 0.833. Now we can find out what the value of the ratio is. The ratio in the question, as we started off with, it is P at pre-fault divided by P at faulted condition. So that's 2 divided by 0.833. which comes to 2.4. So 2.4 is the final answer for this question. 2.4. Well, I hope this has helped. Here's the next question, number 39. The open loop transfer function of a unity feedback control system is given by G of S is equal to K into S plus 1 divided by S into 1 plus Ts into 1 plus 2S. That K is greater than 0, T is greater than 0. So the closed loop system will be stable if we have our 4 options. So this question is taken from control systems subject, and we will have to note that for the closed loop system to be stable, there is a certain characteristic equation that we have to keep in mind. The characteristic equation for a closed loop system being stable is 1 plus g of s into h of s is equal to 0. So here it is given that it has unity feedback control. So h of s is 1. Now let's substitute. We have 1 plus g of s is the system given here, k into s plus 1 divided by s into 1 plus ts, 1 plus 2s into 1 is equal to 0. 1 plus g of s into h of s is equal to 0. So now let's simplify. When we simplify, we cross multiply and get the common denominator and so on and so such. So s1 plus ts into 1 plus 2s plus, we have the second term k into s plus 1 is equal to 0. Now let's open up the brackets and multiply. We have 2 ts cube, so that's s times s times s, 2 ts cube plus 2s square plus ts square plus s plus sk plus k is equal to 0. Now I've opened up the brackets and I have written it down. Now let's take the terms s common. So we have here 2ts cube plus, taking s square common, we get 2 plus t plus s common 1 plus k is equal to 0. So now that we have it in terms of s, let's use Routh's criteria in order to find out the stability condition. So we're going to use using Routh's criteria. We put down the powers of s here, s cube, s square, s1 and s0, and then we start with the table, the Routh's criteria table. So we have s cube here. Now s cube, cube 3 is an odd number, so we write down the coefficients of the odd terms here. So the coefficient of s3 is 2t. Then next the coefficient of s, because this is s power 1 and that's an odd number, so that would be 1 plus k. That's it. Now for s square. For s square, we take the even powers of s. So first term is 2 plus t and the second term is k, because that's a constant, s power 0. Now we will have to solve, or we have to write down the elements for s1 and s to the power of 0, s to the power of 1 and s to the power of 0. So this term here, in order to find that, we have to use the 4 terms above it, these 4. So it is, we always go from the left to the right, always remember that is left to the right. So it's 2 plus t multiplied by 1 plus k minus k multiplied by 2t divided by the first term that we started out with. So here s to the power of 1 would be 2 plus t into 1 plus k minus k into 2t divided by 2 plus t. Now the second element here would be 0. So I hope you're following. This is the first row and this is the first column and this is the second. So the second is 0 here because we don't have the third column's elements here. So this would be 0. This is the first, this is the second. So now for the bottom, s power 0, we do the same thing. We have to multiply this element here with k. So we are moving from left to right again. So this element into k minus 0 into 2 plus t. Now in working on that, we get the result as k. Okay, so we get the result as k over here. Now I think I better write it down here on the side so that you will understand. So that would be like so first. So that's 2 plus t into 1 plus k minus 2tk divided by 2 plus t, this whole term into k, minus 0. 0 into that is anyway 0, divided by this entire term, because that's what we're starting with, divided by 2 plus t into 1 plus k minus 2tk divided by 2 plus t. So in this part, you will notice that we can cancel these two terms out and we are left with k, and that's how we get k here. Okay? I hope you follow there. Now, the next step here is to see, the question tells us that k is greater than 0 and t is greater than 0. Now, for stability, k should be greater than 0. Therefore, this term here should be greater than 0. Okay? I'll write that down here. For stability, the importance is given to k. K should be greater than 0. Therefore, this term here, that is 2 plus t into 1 plus k minus k into 2t should be greater than 0. The entire thing divided by 2 plus t should be greater than 0. If you take the denominator to the other side, it's anyway 0. So we're going to concentrate on the numerator here. Okay? So it's 2 plus t into 1 plus k minus 2k. T is greater than 0. Now, we have 2 plus t into 1 plus k minus 2tk greater than 0. Let's write it in terms of t, taking k common here. So that's k into 2 plus t minus 2t plus 2 plus t is greater than 0. K into 2 minus t, now I'm solving, plus 2 plus t is greater than 0. Now, this would become k into 2 minus t is greater than minus of 2 plus t. So, we need it in terms of k. So, if we are to divide by a negative term, you know that the sign flips over. So, k becomes less than t plus 2 divided by t minus 2. I hope you see what I'm doing over here. Taken k here, so k is less than t plus 2 divided by t minus 2. And to complete it, we know that k is greater than 0. So it lies between 0 and t plus 2 divided by t minus 2. And this resembles option number C. Right. So C is the right answer for this question. I hope it has helped. Here's the next question, number 40. At no load condition, a 3-phase 50 Hz lossless power transmission line has sending end and receiving end voltages of 400 kV and 420 kV respectively. Assuming the velocity of traveling wave to be the velocity of light, the length of the line in kilometers is dash. Okay, So let's first write down what's given to us. We have been given the sending end and receiving end voltages here. So that's Vs is given as 400 kV and Vr is given as 420 kV. Now the question talks about no load condition. So at no load, we need to remember the relation that Vs is equal to A times Vr. Now A is a constant, okay? A is a constant. Let's find out what A is first. So Vs is equal to A times 420. Vs is 400. So from here we can find out what A is. A is 400 divided by 420, which is 0.9524. So now we can write down the equation for A. When we are talking about no load condition and transmission line, A has a formula which is 1 plus YZ divided by 2. The admittance times impedance divided by 2 plus 1 will give you what A is. So these are a few relations that are important and you will have to remember. Okay. So A is a constant with respect to the impedance and admittance. Okay. Right. Now the next step is to expand this. Let's expand this in terms of inductance and capacitance. That's our next step. So A would be equal to 1 plus, now the admittance can be written as R plus J omega L into G plus J omega C divided by 2. Now since the question says that it's a lossless power transmission line, it says lossless. Now for a lossless power transmission line, R and G will be 0. So if R and G are 0, we would be left with 1 plus J omega L times J omega C divided by 2. And J square is anyway minus 1, so we can just substitute that. Here, let me show you. So we have A is equal to 1 minus omega C times omega L divided by 2. Now the next step is to write the equation in terms of phase shift constant and the length. Okay. Now we have another relation. Beta L is equal to root of omega L into omega C. Now here's another relation that will help in deriving the expression that we require. Now here beta is known as the phase shift constant and L is the length of the line, length of the transmission line. Okay, so if we were to square on both sides, if we square it on both sides, we get beta square L square is equal to omega L into omega C. Omega L into omega C, we can substitute it in terms of beta square and L square right here. And we would get A is equal to 1 minus beta square L square by 2. Let's substitute the value for A now. We have A is 0.9524 is equal to 1 minus beta square L square by 2. Now the reason I have brought all of this up is because we require the length of the transmission line. So as many relations that you can remember, it's good to keep them in mind while working on this, because you will have to use some relations in order to substitute them and get it in terms of the unknown variable that we are looking for. Now because we are looking for L, I used this formula here and then substituting that in terms of A to get this. So let's cross multiply and try and get it in terms of beta first. So here we have 2 into 0.9524 is equal to 2 minus beta square L square. So solving this even further, we get beta is equal to 0.3085 divided by L. Now I'm writing it in terms of beta is equal to 0.3085 divided by L, so that we can remove beta. Now beta has another formula. Now here's the next formula. In terms of the velocity of the wave, here, the velocity of the traveling wave, you see in the question there. So in terms of the velocity of the traveling wave, we can write it as velocity divided by F is equal to 2 pi by beta. So all of these are quite interesting relations, in fact. All these relations will do good to remember them. Now let's substitute beta's expression here, because we know what the velocity is, we know what the frequency is. The velocity, according to the question, is given as the velocity of traveling wave to be the velocity of light, right? So from here, we will be able to write the expression for beta as 2 pi f by v. 2 pi f by v. Let's substitute that over here. 2 pi f by v is equal to 0.3085 by L. Okay, right. Now, let's find out what L is. I'll write that down here. L would be equal to 0.3085 into the velocity of light divided by 2 pi f. And that's 0.3085 into 3 into 10 power 8. This is a value that you must remember, divided by 2 into 3.14 into, we have 50. Okay, it's given that is 50 hertz, so it's 50. Solving this, we get 294.745 kilometers. Now once you solve this, you will get it in terms of meters. Please remember, 294.745 meters. You convert that into kilometers because the question asks for kilometers. So here this is our final answer. 294.74 is the final answer. I hope this has helped. Here's the next question, number 41. The power consumption of an industry is 500 kVA at 0.8 power factor lagging. A synchronous motor is added to raise the power factor of the industry to unity. If the power intake of the motor is 100 kilowatts, the power factor of the motor is dash. So since we are dealing with power factor, we have to find out what the power factor of the motor is. We will need both the reactive and the active power of the industry first. So let's write down what we have. We have the power consumption of the industry is 500 kVA. The power factor is 0.8, which means that cos phi is 0.8. Now if cos phi is 0.8, that should tell us that sin phi is 0.6. Okay? They are a team. Now, a synchronous motor is added to raise the power factor to unity, and the power intake of the motor is given. So that's P intake 100 kilowatts. So this is part of the motor rating. We need to find out what is the reactive power as well. So that's our next step. Let's start with the active power. So the active power we'll call that P1, would be 500 times cos phi, which is 0.8, comes to 400 kilowatts. Next, we need the reactive power. The reactive power is Q1, and that's 500 into sin phi, 0.6, and this comes around to 300 kVAR. Now, in order to raise the power factor to unity, the motor should supply 300 kVAR. So this gives us the motor ratings. Okay. So now we have the motor ratings as 100 kilowatts and 300 kVAR. So this is our P, this is our Q. Now for phi, we need the angle now. The angle can be found by using the formula tan inverse of Q by P. This is a standard formula. Phi is tan inverse of the reactive power divided by the active power. So if we substitute the values, we get tan inverse of 300 by 100. So that's tan inverse of 3. So that comes around to 71.56. Now this is the value of phi. We need the power factor, which means that we need cos of this value. I hope you're following. So this is the value of phi. I'm going to write it here. So we have that phi is equal to 71.56. We need the cos of this value, cos phi, which is 0.316. 0.316 is the final answer. I hope this has helped. Here's the next question, number 42. The flux linkage lambda and current I relation for an electromagnetic system is lambda is equal to root I by G. When I is equal to 2 amps and G, which is the air gap length, is 10 centimeters, the magnitude of mechanical force on the moving part in newtons is dash. Okay, so let's start by writing down the relation given to us. Lambda is equal to root I by G. We also have the current I given as 2 amps. We have the air gap length as 10 centimeters. Let's convert that into meters. We have that as 0.1 meters. And we need to find out the mechanical force, F. Alright, so now first we would have to evaluate the energy, because force can be found, the force in an electromagnetic system is equal to minus dE by dx. Now this is an important relation. When we are talking about electromagnetic systems, the force in an electromagnetic system is minus dE by dx, where E is the energy in the electromagnetic system. Now E, on the other hand, can be given by the relation half lambda I. Half lambda I is the formula. So these are the formulas that we will have to use to solve this problem. Okay, so let's start by calculating first what the energy is. Now the energy is half lambda times I. Now we have lambda, we have what I is. Let's substitute first. So we have E is equal to half lambda I, which is half into root I by G times I. Here x is G. You will have to know that x is the air gap length. This is just the formula. You will have to understand in terms of what variable they have given in the question. So here we can write this as 1 by 2 I to the power 3 by 2 divided by G. Since that's 1 by 2 plus 1, that's 3 by 2. Okay. Next, now that we have the expression for E, let's substitute that in here and see what we get. Okay. So we have F is equal to minus of dE by dx. So we are differentiating this. Okay. So that's 1 by 2 into I to the power 3 by 2 divided by g square. We are differentiating with respect to x, which means that we are differentiating with respect to g here. Okay. Right. Now, since this is g square, we will have to minus, becomes minus, right? So here we now have two negatives, which becomes positive, 1 by 2 I 3 by 2 divided by g square. Now we substitute the value for I. We have I is equal to 2, so that's 2 to the power 3 by 2 divided by 2 into g square. Now we have g square here, 0.1. Alright, so let's see now. We have 2 to the power 3 by 2 divided by 2 into 0.1 square. Okay, so now all the values have been substituted. If we solve this, we get F is equal to 141.4 newtons. So 141.4 is the final answer. I hope this has helped. Here's the next question, number 43. The starting line current of a 415 volt 3-phase delta connected induction motor is 120 amps when the rated voltage is applied to its stator winding. The starting line current at a reduced voltage of 110 volts in amperes is dash. Okay, so here we don't have options. We will have to work it out. So let's write down what we have first. We have the starting line current of a certain induction motor. So let's take these values as V1. V1 is equal to 415 volts. And then we have the current given to us. Let's take that as I1, 120 amps. And then we have the reduced voltage. We'll take that as V2, 110 volts. Now we are supposed to find out what I2 is. Okay. Now the ratio is important over here. The ratio of voltages to currents when we are talking about induction motor. So we have V2 by V1 is equal to I2 by I1. This is our relation. Now if we use this in order to find I2 is equal to I1 into V2 by V1. Right? Let's substitute our values. I'll just highlight this formula here. This is the relation that you will have to remember. V2 by V1 is equal to I2 by I1. Now let's substitute. We get I2 is equal to, what's I1? 120 times V2, which is 110, divided by 415. Simple calculation, 31.807 amps. So this is our final answer, 31.807. I hope this has helped. Here's the next question, number 44. A single phase 2 kVA 100 by 200 volt transformer is reconnected as an auto transformer such that its kVA rating is maximum. The new kVA rating is dash. Now there is a very similar question like this in the SET1 paper as well. Let's work it out. Okay, so here we have been given that the kVA rating is 2 kVA, and the voltage of the transformer, the voltage ratio, V1 is 100, V2 is 200. So if we were to calculate the ratio of this, the ratio of the transformer, that's given in terms of alpha. alpha is equal to V2 by V1. This is the ratio of the transformer, two-winding transformer. Okay, so if we substitute, we get 200 by 100, which is 2. So alpha, that's the ratio of the voltage ratio of the transformer, is 2. Now, since the question says that the transformer is reconnected as an auto transformer such that its kVA rating is maximum, now here we can use another standard formula. So when kVA of the auto transformer at maximum rating is alpha plus 1 times the kVA rating of the transformer. We found the turns ratio or the winding ratio or the voltage ratio. It's all the same, which is 2. So here we have 2 plus 1 into the kVA rating given to us is 2. Okay, so 2 plus 1, that's 3. 3 times 2 is 6. So the answer is 6 kVA. So here are two formulas that you would need to remember. One is the winding ratio. Alpha is equal to V2 by V1, the voltage ratio. And the kVA when the transformer is reconnected as an auto transformer, here is the formula. The kVA rating of an auto transformer at maximum would be 1 plus the ratio, the voltage ratio, times kVA. Well, I hope this has helped. Here's the next question, number 45. A full bridge converter supplying an RLE load is shown in the figure. The firing angle of the bridge converter is 120 degrees. The supply voltage Vm of t is equal to 200 pi sine of 100 pi t volts. R is 20 ohms, E is 800 volts, and the inductor L is large enough to make the output current a smooth DC current. Switches are lossless. The real power fed back to the source in kilowatts is dash. Okay, this is not a multiple choice question, so let's work it out. We have been given a couple of things. Let's write that down. We have the supply voltage Vm of t, which is 200 pi sine of 100 pi t volts. This. We have alpha, which is the firing angle given to us as 120 degrees. We have been given R, which is 20 ohms, and E, which is 800 volts. Now the value of L is said to be quite large. It's very large and the value is not given. And the switches are lossless. We have been asked the real power fed back. So the real power is the output power P0, which in simple terms can be written as V0 into I0. Now we need to find out what are the values of V0 and and I0. So there is a general expression for V0 when we are considering circuits such as this. V0 is equal to 2Vm by pi cos alpha, where alpha is the firing angle. Alpha is the firing angle already given to us. Vm is the peak value of the equation given to us, which is 200 pi. So these are some basic formulas. The real power would be V into I, and V0 is written as 2Vm by pi cos phi. So if we substitute what Vm is, 200 pi here, let's see what we get. Okay. So we have V0 is equal to 2 Vm by pi cos alpha, which is 2 into Vm. According to the given equation, we take the peak value, which is 200 pi, divided by pi into cos of 120. So here we get the value as, that's minus 1 by 2, right? So it's 400 into minus 1 by 2. So we have V0 is equal to minus 200 volts. So since we have V0 equals minus 200, let's take the magnitude alone. So the magnitude mod V0 is 200 volts. So we have V0, we still need to figure out the value of I0. So here we use the power balance equation. Power balance equation. Okay, so let's look at the circuit. Now, look at the output over here. Now, this is a place where we will have to concentrate. So, the power balance equation would be E times the output current I0 and the power dissipated by this resistor here, plus the power as a whole, the real power V0 I0. Okay, so I'll write that down here. E into I0 is equal to I0 square R, that's the power across the resistor, plus V0 I0, the real power. So we have the value of E as 800, we don't know what I0 is. We have the value of R as 20, plus V0 we just found 200. Now we solve for I0. So that's 600 I0 is equal to 20 I0 square, and that cancels out. So we have I0 is equal to 600 by 20, and that's 30 amps. Now that we have the value of I0, we have the value of V0, all that's left is find out the real power feedback to source. So because we are finding out the real power, P0 is equal to a simple V0 I0. And that's 200 into 30. 6,000, which comes to 6 kilowatt. That's about it. So now, let's see in what terms. It is in terms of kilowatt. So the answer is 6. Well, I hope this generalization has helped. Here's the next question, number 46. A 3-phase voltage source inverter, as shown in the figure, is feeding a delta connected resistive load of 30 ohms per phase. If it is fed from a 600 volt battery with 180 degrees conduction of solid state devices, the power consumed by the load in kilowatt is dash. Okay, so we have quite a large circuit over here. This is a 3-phase voltage source inverter, and it is feeding a delta connected resistive load here. So this is 30 ohms per phase. Alright, so we are supposed to find out the power consumed by the load. The power consumed by the load, now because we have 3 resistances, that would be 3 into V phase square divided by R. Now this is important. We require the V phase, okay, the voltage per phase. So if we are to solve this further, we can write the voltage, the phase voltage in terms of the source voltage. Now the source is given to us as 600 volts. So this is Vs. Now this is Vs. Now in order to write it in terms of the source, we have P is equal to 3 into root 2 by 3 Vs. Here is another relation. V phase in terms of Vs is root 2 by 3 Vs. Okay, so now if we solve this, 3 times, now root of 2 by 3 is 2 by 3, so that's 2 divided by 3, and Vs square, so Vs square is 600 square, 600 square divided by, now we have R which is 30. Okay, so we solve this to get, let's see now, 24,000 watts, which comes to 24 kilowatts. Okay, though the circuit is quite large, you will have to again come back down to the basics. Now we have the resistive load connected in delta form. So the power that has been consumed over there would be 3 times V phase square by R, because here it's talking about 30 ohms per phase. Okay, so we can now convert V phase in terms of Vs, because that's the source voltage that's being fed from the voltage source inverter. So then we convert that as root 2 by 3 Vs. So these are a few relations that are a must. You will have to remember them. So as much as possible, keep writing the formulas down over and over again in order to work it out. It will help. I'm sure it will. Here's the next question, number 47. A DC to DC boost converter, as shown in the figure below, is used to boost 360 volts to 400 volts at a power of 4 kilowatt. All devices are ideal. Considering continuous inductor current, the RMS current in the solid state switch in ampere is dash. Okay, so this is again not a multiple choice question, so we will have to work it out. The question asks us for an RMS current in the solid state switch. Okay, so we have a relation here. IRMS is equal to IS times T on divided by T to the power of 1 by 2. This is the total time interval T. T on is when the switch is on. IS is the current, the source current, and IRMS is what we are supposed to find out. So T on by root T to the power of 1 by 2 can be written as alpha, and alpha is the duty cycle. This entire term here can be written as root alpha, where alpha is the duty cycle. So IRMS is IS into root alpha. Here is an important relation that will help. So now we need to figure out what alpha is and what IS is. Okay, so for a DC to DC boost converter, we have a relation V0 by Vs is equal to 1 divided by 1 minus alpha, where alpha is the duty cycle. We know what is V0, we know what is IS. V0 is 400 volts, Vs is 360 volt. So let's substitute 400 divided by 360 is equal to 1 divided by 1 minus alpha. From here we can solve and find out what alpha is, right? Let's see what we get here. We get 400 minus 400 alpha is equal to 360. From here, alpha is equal to 400 minus 360 divided by 400. That gives us 0.1. So here we now have the duty cycle value 0.1. Now we need to figure out what the value of IS is. So the question gives us the power as 4 kilowatts. Let's use the power equation to find out the value of IS. So I'll just take another sheet of paper here. Okay, so now we need the power. Let's use the power, in fact. Power equals VS IS. So it's given to us that The question says, at a power of 400 kilowatt, so that's 4000. 4 kilowatt is 4000 is equal to 360 into IS. So IS is equal to 4000 divided by 360, which gives us 11.1 amp. So we have 11.1 amps as IS, and we have the duty cycle alpha as 0.1. So we can substitute that in the IRMS equation that equation that we wrote down earlier. So IRMS is equal to IS into root of alpha. Let's substitute 11.1 into root of 0.1. We solve it to get 3.5 amps. So write that down here, 3.5. Well, this is the solution. I hope it has helped. Here's the next question, number 48. A single-phase bidirectional voltage source converter, VSC, is shown on the figure below. All devices are ideal. It is used to charge a battery at 400 volts with power of 5 kilowatts from a source, Vs, 220 V RMS, 50 Hz sinusoidal AC mains at unity power factor. If its AC side interfacing inductor is 5 millihenry and the switches are operated at 20 kHz, then the phase shift delta between AC mains voltage and fundamental AC RMS voltage in degrees is dash. Okay, so here in the figure we have been given a single phase bidirectional voltage source converter. And if we were to draw the phase diagram of the information given to us, we see that they are asking the phase shift delta between AC mains voltage Vs and the fundamental RMS voltage Vc1. So this is the angle between both of these voltages is what we are supposed to find. Now in order to do that, let's write down all the given information first. We have been given the charge of the battery at 400 volts, the power utilized at 5 kilowatts, the source voltage, RMS voltage at 220 volts, 50 Hz, and the inductor value is given as 5 millihenry. Okay, so I believe this is all that we require. Okay, let me just get another sheet of paper and we'll write it down. Okay, so the given data, given information. So we have the voltage of the battery as 400 volts. The power utilized is 5 kilowatts. 5 into 10 power 3 watts. And then we have the source voltage RMS at 220. And the power factor is unity. So when power factor is unity, cos phi is equal to 1. And the inductor value is also given to us as 5 millihenry. So that's 5 into 10 power minus 3 Henry. Okay, so I'll just put down the phasor diagram here. Okay, so this is the angle delta. Here is the source voltage and here is the voltage of the converter, RMS. And here we have IS, XS, where this is the source current and the source reactance. Okay. Now, the next part is to utilize the power formula. We know in general that the power formula is given as VI cos phi for AC. And in this expression, we are going to work on the source. So it is Vs, Is, cos phi. Now let's calculate what Is is from this equation here. So the power is given to us as 5 kilowatts. So let's substitute the values 5 into 10 power 3 is equal to, Vs value is 220. We need the value of Is, and cos phi is 1. So from this we find out what Is is. Is is 5 into 10 power 3 divided by 220. And that comes to 22.72 amps. So this is the value of the source current. Now let's look at the triangle over here. If we were to find out what delta is, we can use tan. Let's use tan here. So tan delta. Tan delta would be opposite by adjacent value, right? So tan delta is equal to, now the opposite is ISXS divided by VS according to the figure there. Now let's take tan to the other side since we are supposed to find out what delta is. So we get here delta is equal to tan inverse of Is. Now we need XS too, right? So XS can be written as 2 pi FL. Since we have, look at the figure here, we have an interfacing inductor, right? So if we are to write down the reactance of the source, we write it in terms of inductance, L. So 2 pi FL divided by Vs. Now I'll just write down the rest over here for you. So we have delta is equal to tan inverse of Is is 22.72. 2 pi FL would be 2 times 3.14 times 50, since that's 50 hertz, into 5 into 10 power minus 3, all divided by 220. I hope that's all right. You follow, right? So it's Is into 2 pi FL divided by 220. So the tan of this entire thing will give us a delta value of 9.209 degrees. So this is the final answer. Since this is not a multiple choice question, the final value would be 9.209. Well, I hope this has helped. Here's the next question, number 49. Consider a linear time invariant system. X dot is equal to Ax with initial condition x of 0 at t is equal to 0. Suppose alpha and beta are eigenvectors of 2 by 2 matrix A corresponding to distinct eigenvalues lambda 1 and lambda 2 respectively. Then the response x of t of the system due to initial condition x of 0 is equal to alpha is... Okay, so we have our 4 options A, B, C, D. Now since the options are in terms of e power lambda t, that should give us a clue of how we have to form our 2 by 2 matrix. Okay, so the first step, let's note down what's given to us. We have been given the system is x dot is equal to Ax. So that's our first step. Next we have the initial condition at x of 0 at the time t is equal to 0. Now the question asks us to find out the response for the initial condition of x of 0 is equal to lambda. Now when x of 0 is equal to alpha, if x of 0 is equal to alpha, this gives us an initial condition of alpha 0. This is in terms of matrix form. Okay. So if the eigen values are lambda 1 and lambda 2, that tells us that our expression for phi of t, now this is our 2 by 2 matrix. Okay, phi of t is our 2 by 2 matrix. Can consider this to be A. Okay, A which is in terms of phi of t, since the parameter is t. This would be e power. Now this corresponds to an identity matrix. So only our diagonal of the matrix will have elements while the rest would be 0. This is 0, this is 0. So here we have e power lambda 1t and here we have e power lambda 2t. This is because of the two eigenvalues that we have here, lambda 1 and lambda 2, corresponding to the diagonal elements of the matrix. Now the response x of t, now this is important. The response x of t in terms of the initial condition can be written as x of t is equal to phi of t into the initial condition x of 0. Now this is very important. This is the standard expression where the response can be written in terms of x of t, phi of t times x of 0. Okay. Now, x of t is what we are supposed to find. Phi of t is what we have, 2 by 2 matrix, which is e power lambda 1t, 0, 0, e power lambda 2t, into x of 0, which is our initial condition and written in matrix form, that will be alpha 0. Now if we multiply both of these matrices, we get e lambda 1t times alpha plus 0. And the second element would be 0. That's about it. And if we were to write this as a single expression, then x of t is equal to only this element here, which is e power lambda 1t into alpha, finally written as alpha times e power lambda 1t. So this is our final expression or the response of the time invariant system. And this option matches the very first one, A. So here is our final answer. I hope this has helped. Here's our next question, number 50. A second order real system has the following properties. A. The damping ratio psi is equal to 0.5 and undamped natural frequency omega n is 10 radians per second. B. The steady state value of the output to a unit step input is 1.02. The transfer function of the system is dash. So we have our four options, A, B, C, D, and we're supposed to find out the right transfer function for the characteristics given in the question. So we start by writing down the second order system characteristic equation. Second order characteristic equation is given in the form of s square plus 2 psi omega ns plus omega n square is equal to 0. Now this is our second order characteristic equation. It's a general equation. It will be good to remember. And we have been given that psi value is 0.5 and frequency omega n is 10. So let's substitute these values here in the above equation. So we get s square plus 2 into 0.5 into 10 s plus 10 square is equal to 0. And this gives us s square plus 10s plus 100 is equal to 0. Now this is our characteristic equation. Let's see now. The denominator matches with option B and option C. So we have both of these options with the denominator of the characteristic equation here. S square plus 10s plus 100, right? But we have a different numerator. Now in order to find that, we will have to figure out the DC gain. That's important. We need to check the DC gain and see which one matches the given. Here, see, we have the steady state value of the output to a unit step input. So the ratio is given as 1.02. Now we have to check with the options over here which one matches with this ratio here. So the ratio of the output to unit step input is DC gain. Okay, and that would be the numerator divided by omega n square. This is sort of a trick, easy way of remembering the output to a unit step input. You can take it as the numerator of the transfer function divided by omega n square. Now omega n value we already have as 100. So in order to check, now we have ruled out options A and D, right? So it cannot be A, it cannot be D, it has to be either B or C because of the denominator. The denominators of both of these options match the second order characteristic equation that we have just found. So let's just cross off these two and concentrate on just B and C. So we have to check which one of these two will give us the value of 1.02 as the steady state value. Let's start with B first, 102. So if we place 102 here, we get the value of 1.02. It matches. If we place 100 here, 100 by 100, which is 1, it doesn't match, so that's not the DC gain. So that tells us that option B is the right answer. I hope this has helped. Here's the next question, number 51. 3 single-phase transformers are connected to form a delta star 3-phase transformer of 110 kV by 11 kV. The transformer supplies at 11 kV a load of 8 megawatts at 0.8 power factor lagging to a nearby plant. Neglect the transformer losses. The ratio of phase currents in delta side to star side is, so we have our 4 options. Now, we do have a lot of information here, but we will have to be quite careful with what's given to us. Delta star, so it says that 3 single phase transformers are connected to form a delta star 3-phase transformer, and the ratio they have asked is to find the phase currents in delta to star, which means I phase of delta divided by I phase of star. This is the ratio of what we are supposed to find. Now, in general terms, we know or we are familiar with the ratio of voltages and currents. Now, the general relation is V1 by V2 is equal to I2 by I1. Now, if we were to use this in the ratio that we have asked to be found, I phase of delta divided by I phase of star would be equal to V phase of star divided by V phase of delta. Right, they are inversely proportional. So we can easily write it this way. Now, this is because in the question we have been given only the voltages. We have not been given what the current values are. So we can use this. Now, V phase of delta, it has been given that it supplies 11 kV, right? The transformer supplies at 11 kV here, and the ratio is 110 kV by 11 kV. Since we are talking about phase, the voltage phase for a star would be written as 11 by root 3. We divide by root 3 in order to get phasor voltage in star connection. Divided by, now the delta is given as 110. So, 110. So, you will have to keep in mind here delta to star connection, delta side, star side. Okay. So, I hope that is clear. This is star side and that's delta side. That will give you the ratio. So, 11 by root 3 divided by 110. So, that gives us 1 by root 3 divided by 10, and we can reduce that, we can resolve that and write it as 1:10 root 3. 1 divided by 10 root 3 can be written in the form of a ratio 1:10 root 3, and that matches option A. I hope this has helped. Here's the next question, number 52. The gain at the breakaway point of the root locus of a unity feedback system with open loop transfer function g of s is equal to ks by s minus 1 into s minus 4 is a, b, c, d. So we have our options and we will have to find out the value of the gain. Now gain is k. So we have to find out what the value of k is. Let's start with what's given to us. G of s is equal to ks by s minus 1 into s minus 4. Now since we are working with an open loop transfer function, the characteristic equation is given as 1 plus g of s into h of s is equal to 0. This is the characteristic equation, or we can call it a condition. 1 plus g of s into h of s is equal to 0. Now let's work it out with respect to what's given to us over here. We have s minus 1 into s minus 4 plus ks is equal to 0. Let's open up the brackets here. So we have s square minus 4s minus s plus 4 plus ks is equal to 0. Solving further, we get s square minus 5s plus 4 plus ks is equal to 0. Now let's find out what the expression for k is. We take everything else on the other side. We get minus of s square minus 5s plus 4 divided by s. So this is the expression for k. Now the question says that we need to find out at the breakaway point. At the breakaway point. So here is an important condition. At breakaway point, dk by ds should be equal to 0. The differentiation of the gain with respect to s will give us 0. So if we differentiate this expression here, we get dk by ds would be equal to minus of, let's see, if we divide by s here, we can write the expression as s minus 5 plus 4 by s. Now let's differentiate this here. So we get 1 minus 0 minus 4 by s square is equal to 0. So now let's equate this to 0 and find out the value of s here. So we now have, let's see, dk by ds is minus of 1 minus 0 minus 4 by s square. This is what we found. Okay, let's equate and see. We get minus 1 plus 4 by s square is equal to 0. We can write this as s minus s square plus 4 is equal to 0. S square is equal to 4. S is equal to plus or minus 2. So these are the values of s. Plus 2, minus 2. But at breakaway point, we have to consider only the positive value. So this is the valid breakaway point. S would be plus 2. So we have to find the gain at s is equal to 2. So that's our next step. We need to find the gain at S is equal to 2. So here is another formula that would do good to remember. So we have the ratio. So K can be found by calculating the ratio of the product of distances from all poles to the breakaway point. To the product of distances from all the zeros to the breakaway point. Okay, now this is a ratio that you will have to remember. K is equal to the product of distances from all poles to the breakaway point divided by product of distances from all the zeros to the breakaway point. Now, if you need a clue to remember this way, it would be the denominator, the product of distances from all the zeros to the breakaway point corresponds to the numerator. The numerator and the denominator of the transfer function. This is of the transfer function given to us. Okay, corresponding to the transfer function. So, according to the question, look at the transfer function given to us. Ks divided by s minus 1 into s minus 4. Right? Okay, so let me write that down over here. We were given g of s is equal to Ks divided by s minus 1, s minus 4. Now we have the value s is equal to 2. The product of distances from all the poles to the breakaway point corresponds to the denominator of what's given to us, s minus 1 into s minus 4. Substitute 2 in place of s here. That will give us the top part of the ratio of k. And this part, product of distances from all zeros to the breakaway point, is the numerator, and that is just s, because we are finding out what k is, so s remains, which is by 2. So I'll just, let me get another sheet, or I think I'll do it right here, please observe. So we have k is equal to product of distances, right? So that's the denominator. So that's 2 minus 1 into 2 minus 4 divided by s, which is 2. So k is equal to 1 into 2 divided by 2, which is 1. So here 1 is the final answer, and that matches with option A. So I hope the generalization has helped. Here's the next question, number 53. Two identical unloaded generators are connected in parallel as shown in the figure. Both the generators are having positive, negative and zero sequence impedances of J.4 pu, J.3 pu and J.15 pu respectively. If the pre-fault voltage is 1 pu for a line to ground fault at the terminals of the generators, the fault current in pu is dash. Okay, so what we can do first is to try and put it all down in the form of a diagram, so that we have a good view of what's been given to us. So we have two generators here, and the sequences are also given. The sequence impedance is positive, negative and 0. So let me just draw it here for you. So we have the positive, the two generators here, and then we have the negative sequence impedance, and then we have the zero sequence impedance. Okay, so this is J.15, this is J.15, J.3, J.3, and here we have 1 pu given to us, 1 pu as right, as the generator side, and that's 0.4. This is also J0.4. Okay, so we have written down the positive, negative and zero sequences impedance, and let's call the current that passes through here as IA1. Okay, alright, so this is what we have. Now let's say that a line to ground fault occurs at the terminals of the generator. Okay, so now a fault occurs, and when that happens, the diagram would turn into, now here we are writing a equivalent circuit diagram. Okay, we're going to draw out an equivalent circuit diagram here. Let's calculate the values. Okay, so here this is the current IA1, this is 1 pu. Alright, so when a fault occurs at the terminals, this portion here becomes open circuit. Therefore, we have just this impedance, which is the same here for our equivalent circuit after the fault has occurred. The zero sequence impedance will remain as 0.15. Now let's calculate for both these impedances. Now here these two are in the form, are in parallel connection. So 0.4 and 0.4 in parallel will give us 0.2J. You know how to calculate the parallel combination of any resistance as such, right? So that's R equivalent is equal to R1 R2 divided by R1 plus R2. So we can use this in order to calculate the impedances that are connected in parallel here. So 0.4 will give us 0.2, and 0.3 and 0.3 in parallel will give us a value of J0.15. So we have 0.2 as the equivalent positive impedance, J0.15 as the equivalent negative impedance, and J0.15 as the zero sequence impedance. That's because the fault has occurred and it shall remain the same. Okay, so the next step is to find out what the current is, because that's what's been asked. If the pre-fault voltage is 1 pu for a line to ground fault, the fault current, so we are finding out the fault current. So let's calculate the fault current here, IF. Okay, so because we have three sequences given to us, we have the positive, negative and zero sequences, fault current can be found by multiplying 3 times of the current that goes through the entire circuit, IA1, 3 times IA1. This is a good formula, a very useful formula to remember. For a line to ground fault, IF is equal to 3 IA1. So this gives us 3 into 1 divided by the sum of all the impedances that we calculated, 0.2 plus 0.15 plus 0.15, which gives us 3 divided by 0.5, that's 6 per unit. So the fault IF is 6 per unit. This is the final answer. Now let's see if it matches. Oh no, it's not a multiple choice. So the answer, the final answer is 6. Well, I hope this has helped. Here's the next question, number 54. An energy meter having meter constant of 1200 revolutions per kilowatt hour makes 20 revolutions in 30 seconds for a constant load. The load in kilowatts is dash. Okay, so this is not a multiple choice question and we need to figure out by working it out. So let's write down what's given to us first. We have been given the meter constant, 1200 revolutions per kilowatt hour. Then we have the number of revolutions given to us, 20, time 30 seconds. Alright, so we have to find out what the load is in kilowatts. So for this question, it's just a general play of units. We just have to utilize what's given to us and write an expression in which we are left with just kilowatts and eliminate all the rest. So we can do that by writing the expression as, we can start with the number of revolutions here, number of revolutions divided by the meter constant. Now the meter constant is given in terms of revolutions per kilowatt hour. Now we have to accommodate the hours given here as well. So it would be constant divided by 3600, because in 1 hour we have 3600 seconds and we write the time in terms of seconds, okay, into time t. Okay, so this is our expression for the power, the load power. Okay, so let's substitute the values now. We will have PL kilowatts is equal to 20 number of revolutions, and since we have 3600, that goes up to the numerator, divided by the meter constant of 1200 into time, we have 30 seconds. This gives us 2000 watts, which is in terms of 2 kilowatts. Well, I hope this has helped. Here's the next question, number 55. A rotating conductor of 1 meter length is placed in a radially outward about the z-axis magnetic flux density B of 1 Tesla as shown in the figure below. Conductor is parallel to and at 1 meter distance from the z-axis. The speed of the conductor in RPM required to induce a voltage of 1 volt across it should be dash. Okay, so here we are asked to find out what the speed is. Alright, let's write down what's given to us. We have been given the length L as 1 meter. We have the voltage given as 1 volt. We also have the magnetic flux density B as 1 Tesla. Okay, so let's start with voltage induced. Voltage induced will give us an expression in terms of electric field or induced electric field. So the voltage induced is equal to integral of EMdL. This is from 0 to 1. So the voltage induced is equal to the integral of the induced electric field. This is the induced electric field. Okay, so this gives us, now the voltage induced is 1 volt. That's what we have already. So 1 volt is equal to integral of EM dl. So we can write this in terms of EM, or the induced electric field, is 1 volt per meter. Do you see that? So if the induced voltage is equal to the integral of EM dl, now this is in terms of the length with respect to the length. So we write EM as 1 volt per meter. Okay, so that's our EM. Now EM in terms of velocity. Now we will have to write it in terms of velocity. I'll explain why. Let me write it here. Okay. Now we need the speed as n. And n in terms of angular velocity is 60 omega by 2 pi. How do we get this? We get this from the formula omega is equal to 2 pi n by 60, right? So the expression for n would be 60 into omega by 2 pi. But we need what omega is. So omega can be found from this expression. Omega is equal to V by R, where V is the velocity in meter per second and R is the radius of the path. Now V can be written in terms of EM. EM is equal to V bar cross B bar. Now this is the usual notation. So these are the expressions with which we will find out what n is. So we have now written the expression for voltage induced in terms of induced electric field. So we found that EM is equal to 1 volt per meter. Now using this expression here, we will get what V is. So V is the radius of the path times angular velocity. So EM, I'm going to use this now here, okay? So EM is equal to V bar into B bar, right? So this is 1 volt per meter is equal to V into 1 Tesla. So V is equal to 1 meter per second. Alright. So from this expression here, this angular velocity is equal to the velocity for meter per second divided by the radius of the path. We get R is also 1 meter according to the figure given to us. So R is equal to 1 meter, V is equal to 1 meter per second. That gives us omega is 1 radian per second. If V is 1 meter per second, radius is 1 meter, so that gives us an omega of 1 radian per second. So we have omega, V, R. Now let's see if we can substitute here. Oh, we just need omega here. So n is equal to 60 omega by 2 pi. 60 into 1 radian per second divided by 2 into 3.14. So the speed would be 9.55 per minute. So this is the final answer here, 9.55. 9.55. Well, I hope this has helped.